Earth science time. We're talking about the properties today of the atmosphere. Properties of the... Ooh, we'll do it fancy like this.
What is that?
He said fancy letters. The M.
Oh, he's got his little tails hidden. That's how I know how to do this.
Oh, graffiti?
No.
Oh,
Well,
liar.
There we go. Properties of the atmosphere. We're going to talk about 4 things. Well, I don't know, 3 things, and then kind of like a fourth is nestled into another one. So the first thing we're going to talk about, temperature. So there are 3 main properties of the atmosphere. Like there are other properties of the atmosphere. Like color is a property of the atmosphere, but it's not a really useful or important property. The 3 useful and important properties, and the fourth kind of nestled in there are what we're going to talk about today. The first is, well, let's see if you can guess. What's one important property we commonly talk about the atmosphere? Temperature. Temperature. We talked about this in physical science. We talked about this in 8th grade science. We talked about it a little bit yesterday. Give me a good definition of temperature relating to the motion of the atoms.
A measure of the average kinetic energy of the particles in a material.
Yeah, what's suspicious about your definition is I can see your thumb moving along the definition. Okay, but that's okay. You're right. That's exactly what I was looking for. We could say it's a measure of the average energy of the particles. I'm going to specify kinetic and potential energy, because it does depend on the potential energy a little bit as well. You guys remember talking about kinetic and potential energy in physical science, right? Mm-hmm. Kinetic energy is the energy something has because of its motion. Potential energy is the energy something has because of its position. Both of those, of the atoms, play a part in what the temperature is. And just so that we're clear, if a group of atoms is moving on average faster and further apart, that is higher kinetic and higher potential energy, what's going to happen to its temperature? Increase, yeah. So the higher the motion of the particles and their position, the higher the temperature. More motion means higher temperature. So they can never stop, but when they have the very lowest kinetic energy and potential energy they can possibly have, is there a special name for that? There is. What is it? Remember? What temperature is that? When they have the absolute minimum kinetic and potential energy. 0 on one scale, or 0 on the Kelvin scale. Do you remember what this is called?
Oh, I know what it's called.
Absolute zero. You got it. Yeah, absolute zero. So when there is a minimum temperature, the minimum temperature is when these 2 things are as low as they can possibly be for a group of atoms, and that's called absolute zero. So the temperature of the atmosphere, why is it important to talk about this? Yeah, right. This is probably the thing regarding the atmosphere. This is the thing that we as human beings talk about the most, right? What's the temperature outside today? Cold enough that I had to wear a coat when I walked my dog, so I think it said 14 degrees Fahrenheit on mine.
Just a coat?
Well, I had pants on. 14 degrees Fahrenheit it said on my little thermometer.
At this moment?
Colby, the YouTube video, we're not going to say inappropriate things. Now I'm going to have to cut this, and that really, really aggravates me because it changes my planning period from a nice, pleasant time to having to edit videos, Colby. Let's move on to the next thing. Temperature. So we talk about the temperature of the atmosphere to know about the average of its particles. And I want you to remind you of what Hannah said. We're asked about what would the temperature be of a planet with no atmosphere? Well, if there are no particles, what's the temperature? Yeah, there's no temperature. It's not the same as it being 0. It's that there is no temperature, right? In the same vein as like in math, there's a difference between your answer being 0 and the answer being no real numbers. Is that a real thing? Or no real solutions? What do you call it with the 0 with the line through it? Yeah, cannot finish, right? It's the difference between having your lap time be 0 seconds and your lap time be D and F, right? So temperature has to have particles to measure, right? What's the temperature of space? That's really a meaningless question because there are very, very few particles in space, and what ones there are have all crazy. Some of them are moving extremely, extremely fast, and so that would make it seem like the temperature should be high, but there are so few of them that it's not really a meaningful question. How do you measure temperature? What tool do you use to measure temperature? A thermometer. What are the scales we use to measure temperature usually?
Fahrenheit, Celsius, and Kelvin.
Fahrenheit, Celsius, and Kelvin. Because this, sometimes people don't know this by the time they graduate, and that's embarrassing to me. Let's talk about the freezing point of water. Point of water. The boiling point of water. In each of our 3 scales we just mentioned. Degrees Fahrenheit, degrees Celsius, and Kelvin. I don't normally touch on this in earth science, but like I said, it's embarrassing to me when someone who's a senior says, doesn't water boil at 107 degrees? I'm like, what? No, it doesn't. Well, I'll give you a hint. It's not 107 for any of these. Does anyone know what the freezing point of water is in degrees Fahrenheit?
32.
It's 32 degrees Fahrenheit. What's the boiling point of water in degrees Fahrenheit?
12.
Just save you the embarrassment. 212 degrees Fahrenheit. You know it for degrees Celsius? I hope you know it for degrees Celsius.
0.
0 degrees Celsius is the freezing point,
And 100.
and 100 degrees Celsius is the boiling point. That's how the Celsius scale is defined, is by those 2 things. And make sure you didn't write degrees Kelvin. Remember, Kelvin is a unit on its own. It's not degrees Kelvin. And do you remember the conversion from degrees Celsius to kelvins?
It's like
It's like something with 70.
273.
Yep. So the freezing point of water in Kelvin is 273.15 Kelvin, and the boiling point of water is 373.15. That's not really a 5 Kelvin.
Do we really ever use Kelvin?
In science, we use it the most because what's nice about this scale. What's 0 Kelvin? We talked about it a second ago. What's 0 Kelvin?
Absolutely.
Absolute 0. Can there ever be a negative temperature on the Kelvin scale? No, by definition there can't. And so this makes it nice to do math with because we can't have negative numbers. A lot of the equations that we use that involve temperature, a negative number would throw everything off because we'd come out with answers like negative mass, which can't exist, or negative volume, which can't exist, right? So we use this the most for when we're doing math with temperature. It's not very convenient for like, how hot's my soup? Because it's got these big janky numbers. But it is really, really, it's not only convenient for math, but it's the only one of these that works for math at all because it doesn't have negative numbers. What's human body temperature?
It's like 86.
Let's try again. 98.6 degrees Fahrenheit.
You're 80.
Something when this scale was invented, the man who invented the Fahrenheit scale defined 0 as 0 degrees Fahrenheit as the temperature, the coldest temperature he could get in his laboratory, which was with a mixture of salt and ice and water, was 0 degrees for him. And then the boiling point just happened because his other definition, so he defined 0 as that brine solution, right, salt and water and ice, and 100 he defined as human body temperature. So that was his scale. Whereas Celsius was 0 was the freezing point of water, 100 was the boiling point of water. Fahrenheit was based off of 0 is the temperature of the brine in his lab, and 100 is his human. You know now, the human body temperature is not 100 degrees, or at least not usually, right? It's 98.6. And so this scale, janky. Let's not use this. What's nice about this, there is one nice thing about the Fahrenheit scale, and it's that if I say that the temperature outside is in the 50s, that you know what that means, right? So for one thing, you have familiarity with it, and for another, they're like each little group of 10 on the scale is like a totally different way that human beings can feel, right? So it actually is very useful for when we're talking about outside temperatures, but that's about it. It's based off of something weird and something wrong, so let's just erase that one. In fact, let's erase them all because we're going to move on to the next thing. What is another property of the atmosphere besides its temperature? Pressure. Air pressure. Let's write that down. Air pressure. Number 2, air pressure. Let's define air pressure. Can you think of a way we can define that?
The pressure exerted on the surface by the weight of the atmosphere above the surface.
Yeah. Okay. We can't really use the word pressure to define pressure, can we? So if you remember from physical science, this is the calculation we use in physics for pressure. P, pressure, equals F divided by A. P is pressure. What do you think force is? Well, it's force. F is force, measured in newtons. A is, guess, area, measured in, what do we measure area? What would be the base unit for meters? Squared. Meters squared is area. So we measure pressure in something called newtons divided by square meter, which is equal to a Pascal, which is abbreviated PA. And a Pascal is a really, really small unit. A newton is about the weight of maybe 10 paper clips, a little handful of Cheerios or something. A newton is a small, small weight, small, small force, and it's divided by a square meter, which is really quite a large area, right? A meter is about 3 1/3 feet. And so an area of 3 1/3 feet by 3 1/3 feet, right, with a tiny little weight on it, this is actually a very, very small unit for pressure. So a lot of times we'll use something called kilopascals, which is more useful because it's a bigger number, right? Kilo meaning 1,000. So we measure pressure in the SI in kilopascals. But another common way that we measure pressure on Earth or anywhere else is called atmospheres. We sometimes use atmospheres, where 1 ATM, atmosphere, equals 100,000 pascals. So those ATM, atmosphere is what we, and that the definition of this unit, atmosphere, is the pressure exerted by the atmosphere of planet Earth at sea level. Because you know, the atmosphere, we a lot of times think of, like, if I ask you, what's in your cup? You might say, nothing, right? But it's not really nothing. There's air in there, right? The atmosphere exists. We a lot of times, since we exist our whole lives in the atmosphere, a lot of times we think that the atmosphere is just nothing. But the atmosphere is matter, and it has a certain mass. And actually, the atmosphere is quite tall, right? It's several miles tall to the place where we consider it to be ended. And so it exerts a lot, it has a lot of mass, and because of gravity, it exerts a lot of force on planet Earth. It's this much force, right? Like I said, we're used to it, so we don't normally think about it, but pressure is exerted on us all the time. Let's talk about next. This is the kind of like side note one. We'll call it 2.5. Density. And density depends on air pressure and temperature and the other one, but the density of the air, and really, when we talk about weather, this one actually becomes the most important, it's the easiest to talk about, but it's not something we talk about as a strict, like when we're talking about the properties of the atmosphere outside right now, we don't normally talk about what the density is. What's our equation for density? Do you remember?
M over V?
Yep. M over V equals what? Density. Yeah, what was the abbreviation for density?
Oh,
Rho. I'm gonna. Oh, before I read this to you, what happens to the density of the air as we go up? As altitude increases. As altitude. Good grief! I can't spell a single thing. As altitude increases in the atmosphere, density decreases. And unlike temperature, which we talked about in the last lesson, this is a strict relationship. For the most part, almost always, as we go up in the atmosphere, the density decreases. Near sea level, it says, near sea level, the density of air is about 1.2 kilograms per cubic meter. Write that down. The atmosphere has a density of about 1.2 kilograms per cubic meter. We talked a second ago about what a square meter looks like. What would a cubic meter look like?
Where did you read that?
The density of the atmosphere, I'm on page 290. The density of the atmosphere, the density of air is about 1.2 kilograms per cubic meter. So a cubic meter would be about, yeah, it's a cube. So it's a cube with all the sides being 1 meter long, right? And that has a mass of how much? That 1 cubic meter of air, 1.2 kilograms, right? And 1.2 kilograms is not nothing. That's about 3 pounds. It's not a lot for that big of area, or sorry, that big of volume. but it has some mass, right? There's matter in there. There's matter in there. Pressure, temperature, density relationship. Let me read this to you. In the atmosphere, the temperature, pressure, and density of air are related to one another. Imagine a sealed container containing only air. Are you imagining it? Imagine a sealed container containing only air. The pressure exerted by the air inside the container is related to the air temperature inside the container and the air density. So if we increase the temperature of that sealed container of air, maybe imagine a balloon, if we increase its temperature, what's going to happen to the pressure it exerts? It's going to increase, right? What's going to happen to its density? Now listen carefully, be careful. So the balloon here has a certain amount of air in it, right? As the temperature increases, what's going to happen to the balloon, first of all?
It's going to get bigger.
It's going to get bigger. But what happened to the amount of air in it? Is it the same amount of air?
Yes.
Yeah. So it has a certain mass, but now we're dividing that mass by a bigger volume. What's going to happen to its density? Decrease. So as temperature increases, I'm doing this so I want you to write it down. As temperature increases on a gas, density decreases. And then also write down what Levi said. As temperature increases, what happens to the pressure? You said it right already. You remember what you said? Pressure increases.
So what? Temperature decreases.
Temp up. So as the temperature increases,
Oh.
the density decreases,
Yeah.
but the pressure increases. Think about it, because what's going to happen?
It's gonna pop.
It's going to pop. Eventually, if we heat it up enough, the balloon will pop because the pressure has gotten too high. So as temperature increases, two things happen. Density goes down, pressure goes up. We're going to talk about the last property before we talk about wind. And then there's another thing that's in your lesson called temperature inversion that you'll have to read about on your own, but I trust you. Yes? Yes. I'm going to erase this, and then we're going to move on to humidity. Humidity. So write it down, please.
Humidity?
You're saying it weird.
You know, I said it like this a couple of years ago when I taught this lesson for maybe the third time, and I thought that's a hilarious way to say humidity. I thought that is hilarious to say it, humidity. And then I told my grandparents that I don't know. I talked to them. I was like, I thought it was so funny when I told my earth science kids it's called humidity. And then my grandma said, your grandpa has pronounced it like that his whole life. I was like, well, maybe that is where, maybe it's genetic. So the humidity, you know what the humidity is. What is it?
Amount of like water in
Yeah.
the air.
Good. I'm going to use that exact definition. Amount of like water in the
Thank you.
air. It's fairly simple. The humidity is something we kind of understand innately, right? You can tell. I can tell in my nose. You can tell when it's humid outside, right? You might humid. What we're going to talk about is the two ways that we commonly use to measure humidity. They're called dew point and relative
Dew point?
humidity. So to understand either of these, you need to know that there's a certain amount of water that can be contained in the air before what happens. What's going to happen if we get too much water in the air, like in your lab? It will, what? Yeah, it'll precipitate. The water will precipitate out. So write this down. At a relative humidity of 100%, at 100% precipitation, I'm going to write can occur, because there are some other things that come into play there, but precipitation can occur. And it also can occur lower than 100%. But this is basically, when it's at 100%, the air is holding as much water as it can, right? There's a maximum amount of water the air can hold, and at 100%, obviously it's holding as much as it can. What do you think can hold more water in it? Warm air or cool air? Yeah, warm air, I'm going to make this a little side note. Warm air can hold more water than cool air. And I put this in a side note because we're going to use this, I can't remember if it's in the next lesson or in the next chapter, but yes, it's in the next lesson. So keep this in your brain because we're going to talk about it again tomorrow in quite a bit more depth. But warm air can hold more water than cool air. And so relative humidity is just at whatever temperature the air is, how close is it to full? How close is the air to full of water? For a given temperature, not a given temperature.
And this is under relative humidity?
Yes. How much water the air is holding compared to what?
How much it can.
Yeah, exactly. How much it can hold. And then that times 100%. Same thing as like, this thing is just like when on your test, maybe there are 70 points available on the test, and you get 60, right? It's how much you did get divided by how much you could have gotten times 100. That would be your percentage. For a given temperature, I know I got to the bottom and my handwriting really took a dive. For a given temperature, how much water the air is holding compared to how much it can hold times 100%. So if we say the relative humidity is 50%, how much water is in the air compared to how much it can hold? Half, right? Yeah, it's holding half as much as it could hold. Does relative humidity kind of make sense to you? To me, this is the easier one. Okay? Does this one make sense though? It's just a comparison of how much water is currently in the air compared to how much it could hold at that temperature. And if it gets to 100%, it probably will precipitate. A nice comfortable humidity I said it wrong. Humidity for people to like exist in and not get a bloody nose is like somewhere between 30 and 60, I would say, right? People can get uncomfortable when it's 100% humid or like 99% humid and your hair can do crazy things. One time when I got off the airplane in Fort Lauderdale, Florida, I felt it in my glasses and in my sinuses and in my hair. I was like, this is like swimming. It's like so humid all the time. I was instantly drenched in sweat. It was disgusting. Because the worst thing was that warm air can hold more water than cool air, and it was 105 degrees when I went to Mexico. This is 105 degrees, but it was still 95% humid, and so the water was, it was just like being at Whitney Lake under the water. Like it was wild. You should have seen my hair. I'm just kidding. My hair doesn't really respond to that, but I imagine probably yours does, Dally. You would have looked like a chinchilla. Anyway, we're gonna talk now about dew point, but the relative humidity makes sense, right? Dew point is for the current humidity. Humidity. For the current humidity, what temperature would that amount of water be 100% humid? So I phrase that kind of weirdly. I don't know a better, maybe your book has a better way of phrasing it. Let me read what your book says. Another common way of describing the moisture content of the air is the dew point. The dew point is the temperature to which air must be cooled at constant pressure to reach saturation. Saturation is what I'm saying is when it's full of water, right? And so we have a certain amount of water in the air right now. Bueno, you're with me so far? You want me to read it to you? Because you can't read it?
Does that say amount of water be 100%?
Be 100% humid. We're going to stop there because the bell rang. Look up relative humidity or dew point on your own. Have an excellent rest of your day.